Thank you for joining this webinar from the Engineering Integrity Society. I will now hand you over to the Chairman of our Young Engineers Forum, Jonathan Joy, for an introduction to today's presentation.
Thank you very much, Sarah. Thank you everyone for joining us today. We're really excited to have an excellent speaker with us today, Damian Harty, who's going to be giving a presentation today about the myth of accuracy. As Sarah stated, this is part of the Engineering Integrity Society's Young Engineers Forum. We hold regular seminars and webinars to help those and support those who are towards the beginnings of their exciting engineering careers. We plan to have more of these events over the coming weeks and months. So if you have enjoyed today's offering and want to see more from us, then please get in touch with Sarah. Her email address is info@eis.org.uk. We'll try and get that up in the chat so that you can get a copy of that at some point during the presentation. So on with the presentation itself. Damian will be speaking for around half an hour. If you have any questions that are prompted from Damian's discussion and from what he presents, please do give us your questions. He would be delighted to answer as many as we can. If you can put your questions into the group chat, then Sarah can collate them as we go and we'll present those at the end. We'll also have a record of them. Should we run out of time, we can make sure that everyone's questions will duly get answered. So, moving on to the presentation itself, Damian Harty. Hart is a renowned individual within the automotive community. He's worked for a number of companies, including Ford, ProDrive and Tesla. He has led the design and development of vehicle chassis and vehicle dynamics through the initial simulation phases right through to release and sign off. And he's a published author of multi-body modelling and has a highly technical approach to the way that he handles his work. So, as I said, we're very excited to have you here today, Damian, and I'll let you take it away.
So I hope that you can all see this window now, the title slide. Let me know if that's up there. This kind of little lecture is something that I first gave over 20 years ago. I was invited by the Engineering Integrity Society to kind of come and talk about something thought-provoking and interesting. And so I thought I would talk about this idea of the sort of misplaced pursuit of very high levels of accuracy. One of my favourite quotes is from the famous American statistician George Box, who said, "All models are wrong and some models are useful." And I think a lot of people have a problem accepting that models are wrong, but that doesn't actually make them useless. And so I got over the fact a long time ago that all of my models are wrong and set about trying to make them useful. And this talk really is about trying to come up with a philosophy for where you draw the line with the kind of complexity and depth that you go into when you're modelling things. I've got a pretty long career, even longer these days, in all sorts of kind of somewhat interesting things for vehicles with wheels and tracks as well, actually. You can see there's some motorcycle video there. I recently posted a very short version of this video on LinkedIn and was astonished by the amount of interest that it got. A six-wheeled vehicle climbing over a step there, that's a standard battlefield mobility test for a military vehicle. They have to kind of muscle up to a step and then climb their way over it. This was a study for a vehicle with 6 in-wheel motors. There's a model of a drifting rear-wheel drive car. For some reason, I'm quite fascinated by drifting things. And some of the other vehicles I've been involved with, some of the there's a racing Aston at the top left. the late adventures of the Subaru World Rally and the Mini World Rally car, which was particularly fascinating. That was a real joy and pleasure to work on. And a number of projects for Triumph, a lot of quite detailed modelling for Triumph. And also a lot of detailed modelling for Polaris as well, also on the motorcycle side. So I've touched a kind of a really wide spectrum of vehicles, and so I'd like to think that my conclusions are kind of somewhat generic across a wide set of applications. So I will just step in, if I can persuade that to go. So it's really easy to believe that there's this specious correlation between making something accurate and it being useful. And so this kind of green line is what people draw in their heads. Implicitly, they presume that if something is less accurate, it must somehow be less useful. And my argument is that if you think like this, it can cost your organisation a lot of money, and I'm going to lay out my reasoning for that. What I'm going to lay out is not particularly complicated, but it is perhaps a little bit counterintuitive. This is an example that I quite like to talk about. This was the Tay Bridge across the Firth of Tay in Scotland, and it collapsed. It was a rail bridge built of quite a lot of steel. In 1849, it collapsed. I don't know exactly which year it was built. It collapsed with a train on it, and unfortunately that cost 75 lives. And the collapse was attributed to the absence of crosswind loads in the design calculations. So it had been all very carefully calculated for the kind of the weight of the bridge and the live load of the train crossing and so on. But not enough attention had been paid to the wind loading, which of course can be quite high up in the stormy Firth of Tay in Scotland. So we can talk then about accuracy. What do we mean by accuracy? And for me, I mean there's the absence of a numerical difference between the behaviour you predict with some kind of model and the behaviour that you measure. And this is what I'm talking about when I use the word accuracy. So it's not a yes or no thing. The absence of accuracy we might call error, and error is a sort of a sliding scale that can go from 0 to a very large number, and it can be any of the values in between. And quite a lot of the time people talk about percentage error, and they're quite happy talking about a 1% error, or a 10% error, or a 20% error. People understand what those ideas mean. So for me, I want to get across the idea that there's this kind of, black and white binary state. For accuracy, that's not the case. It's not a binary state. It's a sliding thing, and it's really about the kind of the degree of inaccuracy. And once you start framing accuracy like that, it helps you think in a slightly more, I'll say, continuous way about the level of accuracy that you're pursuing. There's a couple of questions that this generates. One of them is the measured data what actually happens if you don't measure it? And for example, in refinement circles, it's well known that when you glue an accelerometer onto something, you mass load the thing, and therefore you change the behavior of the system. And so the measurements you get are not the natural behavior of the system, but they're as close as you can get. And perhaps if you think about it a lot, you can compensate for some of these measurement effects. But some of the measurement effects are much more subtle than that. For example, if you put a camera in someone's car to record how they drive, it's somewhat likely that, to start with at least, they will modify their driving behavior because they will be aware of the fact that they're being recorded when they're not normally. And so there's a whole range of questions to be asked about whether what you measure is the same as what happens if you don't measure. And I'm sidestepping all of that, but it is good to be aware that those questions actually exist. And then the other question is what you measure what actually happens in service, and particularly with sort of fatigue and durability questions. it's typically true that we don't really know exactly what our customers are going to do. And so what we end up doing is guessing what they're going to do and then putting some pieces of concrete in a proving ground and driving the vehicle over these artificial lumps and bumps and hoping that correlates with what our customers actually do. And if we're in an established company, we can at least get some kind of data for what our customers have done in the past. So if we're a very established company, we might well have good records of what our customers have done in the past. But if you look at, let's say a new vehicle where you've improved the capability, then what your customers did in the past might not be what they do in the future. And so even when you've got a good historical database, it can be difficult to guess what's going to happen in service. And again, I'm sidestepping that question. I'm saying that we have to be aware of it, but in the end, what we need to do with our design process is draw a line in the sand and make our best guesses at everything, and then move forward with those guesses. So, like I say, I'm sidestepping those questions, and I'm just coming back to this idea that there is something that we can do and measure, and there is something that we can model and predict, and accuracy relationship between what we measure and what we predict. And of course, if we can't measure it, we have really no idea whether we're accurate or not. So this is another example. This is only 75 years after that first example. So that's basically a single human lifetime from a rail bridge carrying steam trains blowing down because we forgot to think about them to a 4-passenger transatlantic jetliner. And I think that's an astonishing span of achievement in a single human lifetime. I apologise that the quality of the image is a little bit low, but nevertheless, this was the prototype Boeing 707, which of course later morphed into the whole family of Boeing 7 Series airliners that are many of which are in service today. It very famously did a barrel roll at an airship, actually finding the clip of the pilot on YouTube talking about this barrel roll. He was told to put on a good show, so he didn't tell anyone that he was doing this. And he famously rolled it over the air show. So you can see there's that photograph out of the window of the plane upside down. That stunt got them a lot of orders, and so clearly whatever the design process was for this, it was good enough to actually put the plane into service. Let's talk about usefulness then, because I talked about accuracy and I talked about usefulness. I'm saying that what I'm calling how we can use predictions to our advantage during the design process. And this idea of being able to use the prediction advantageously is really key to understanding the message that I'm trying to put across today. If we're not going to use predictions during the design process, then we should, as engineers, ask questions about why we're doing them, because the predictions are using up the resources of the company. And if they're not for anything, then perhaps the resources of the company are spent doing something else. And that really applies whether we're a one-man band or a multi-billion-dollar intercontinental transnational company. That question still really applies and needs to be asked. Also, if the predictions are too late to influence design decisions, then they're also not useful. You can argue that they maybe make a sort of a bank of knowledge for future activities, and maybe they do, but the current activity will be repeated as is. So I'm a little bit cautious about that as an argument. What we really need are predictions that are available in time to influence design decisions. And a decision that arrives after we've committed tooling and after we've committed irrevocably to some route, it's no good telling us afterwards that actually it would have been better to do something different. What we have to do is keep walking down the path we're going. And that's a particularly key thing that I think maybe a lot of younger are not necessarily exposed to. And I think this idea that we have to and that a less accurate result but in a more timely way is actually more valuable. I think that's the counterintuitive thing that I'm trying to put across here. Having talked about what I mean by accuracy and usefulness, I want to talk about how they relate. And so to start with, we can draw a little graph, and I can put in some constants. This is just a little formula typed into Excel to draw this curve of diminishing, which a lot of people are familiar with in principle, and most people would sketch something like this. And the only reason that I've represented it algebraically is because of something else that I want to do later. This is not any kind of perfect mathematical model of really anything, because it's quite difficult to measure all of these things. But it's a visualization, I'll say, using an exponential function. It's the same exponential function that describes charging a capacitor, and you can represent it with a first order differential equation as well. But I've just got this little exponential function here. And I've obviously scaled things for percentages rather than integers. And this is quite like, sometimes people talk about a Pareto distribution. They talk about 20% of the stuff giving you 80% of the value. You can see that is broadly true with this little curve that I've sketched here. And again, I don't want to claim anything too authoritative for this, but I just want to illustrate this principle that initially you put in maybe 10% of the effort, and you get perhaps 50% of the reward that you're trying to do, and then the remaining 50% takes the remaining 90% of the time. And this is an experience that's intuitively familiar to many of us. So one of the things I suggest is that usefulness is about the absence of duration, if you like. So I'm going to say, well, I'm just going to construct a little hyperbola here, a little kind of y is 1 over x sort of function, and I'm going to basically argue that if we know an answer that is good enough to make a decision earlier, then we have the opportunity to do something more useful with it. Perhaps we can use that knowledge to ask a better question. Perhaps we can allow that knowledge to take us in perhaps a different direction to the direction we're going to take. But the bottom line is that I assert that the sooner you know something, the more useful it is. And that does lead to another conclusion later as well. Now, basically, if we combine those two descriptions, we end up with something a little bit like this. If the usefulness is the kind of the accuracy divided by the duration, and the duration is this exponent function, we end up with a curve that looks a little bit like this. And again, I'm not claiming any perfection in this result, but what is interesting for me is that it's definitely true that after an initial increase in accuracy promoting a very steep increase in usefulness, we go past some kind of maximum, and it starts to curve downwards in an ever accelerating way. And so if I presume that in order for the thing to be useful, it's got to pass a certain level of accuracy, then probably that level of accuracy is past the 50% point on this graph. And we can see very, very clearly that having excess accuracy starts to make the thing less and less useful in an ever accelerating way. And this slightly counterintuitive relationship is something that we should keep in mind and use it to avoid accuracy. So I'm not advocating 80% error in all calculations, definitely not. That would get me fired and shorten all of your careers fairly quickly. It's an artifact of the particular values that I've chosen to draw this piece of algebra and to illustrate the point. There's probably a threshold level of accuracy, as I said, that whatever we're doing has to pass. So the method has to be accurate enough to support the decision that we're trying to make today. It's a very important point that what we need to be doing is supporting today's decisions today, and not necessarily getting ready for decisions that are some way in the future, because there's a lot of uncertainty between now and the future. And so spending a lot of resource to be ready for them is not always the wisest thing to do. So we should definitely prioritize the decisions that are being made soonest, and we should pursue those. And we should be able to think about these and give ourselves some idea of how accurate we need to be. And as an example, there's a written paper that accompanies this presentation. I talk about the example of deciding whether or not to use different sized tyres on the front and rear axle of a vehicle, called weight distribution. And I wrote this kind of sample many years ago as just a sort of a made-up exercise. But in fact, a few years ago, I did it for real with my current employer. We had a recommendation from an external consultancy that we needed to put on bigger tyres on the rear than on the front, and the difficulty that gave us was that it halved the volumes of each tyres and quite significantly put up the prices, and also gave us logistical problems. You have a problem that if the wheels are interchangeable, then it's quite easy to put the tyres the wrong way around, and so on and so on. So there's a number of reasons why you'd like to keep the tyre sizes the same. When we're talking about these tyre sizes, there's only a certain resolution. One size tyre is 225 millimeters wide. The next size tyre is 235 millimeters wide. And so it doesn't make sense to calculate whether we need a 225.2 millimeter tyre or a 225.3 millimeter tyre. It absolutely doesn't matter, because the choice that's available to us, the resolution of the decision, if you like, is relatively low. So we only need calculations that can discern the consequences of the decisions we're making. And it takes quite a lot of discipline to stop when you know that your calculations could be better and could be more accurate and so on. It's in our nature, all of us who do this kind of work, it's in our nature to keep pursuing, have to resist that. So my message here really is that we shouldn't be pursuing unnecessary accuracy. And there's a lot of critical thinking and skill that needs to be made in determining what constitutes unnecessary accuracy. But nevertheless, if you start switching your thinking in this direction, then my experience is that it does yield a lot of benefits. And it actually, it turns into a bit of a game of what's the worst possible model that I can use and still answer this question. And sometimes the results to that are very surprising. The thing to stay away from is this sort of habitual addition of complexity to a model, which is very easy, and it's particularly easy if you're using an existing model or a template that you've bought from a commercial provider that has a very large number of parameters and data input. It's very easy to say, I can't do anything until I've got all of the numbers that go into this model, because until then the model won't be accurate. And that's really the most kind of miserable subtraction of value that you can put forward in a process. And so my advice always is to try and guess all of the information that you haven't got, and then to very quickly, because of course guessing doesn't take long, very quickly start doing some sensitivity calculations to all your guesses. And what you'll find is that of the 10 guesses that you made, 7 of them don't really matter, and the other 3 you can put in priority order. And that means that you can start pursuing into getting that information in really priority order to add to the usefulness of the analysis that you're doing. And the example that I habitually use, which is a little bit flippant but hopefully makes the point, is if you have a list of 100 parameters in alphabetical order and you work your way down the list, it'll be a long time before you get to yaw inertia. But if you actually do any vehicle dynamics analysis, you'll understand that the yaw inertia is really important, and so it should come to the top of your list. And if you don't do this sensitivity study and prioritization of the information that you're chasing, you'll always be in this position where you're still collating information while people are looking for answers to support decisions. And that sort of thing gives analysis a very bad name. And that's why I give talks like this, to try and break people out of that style of thinking. So one of the things that I say in my book is that I think that the most cost-effective analysis is remembering and understanding what has gone before. I think, first of all, just remembering things is very helpful. If you can remember that a typical SUV yaw inertia is about 3,500, 4,000 kilogram meter squared, that can help you get in the right Paris to start doing some sensitivity analysis. Whereas if you can't remember whether it was 4 or 4,000 or 4 million, then that's less helpful. And understanding what went before is important as well. If you think that your experience of the torsional stiffness of a ladder frame vehicle, an industrial ladder frame vehicle, it applies to a passenger car monocoque, then you will be very disappointed when you set some torsion targets for the passenger car with its performance compared to its competitors. And equally, if you don't understand that difference the other way, you'll end up setting impossible targets for your ladder frame vehicle. So it is really important to understand how what you've done fits into the big picture. And I'm hugely fortunate in that I've had exposure to a very large number of different classes of vehicles operating under very different circumstances. And so that helps give me some sense of the big picture, if you like, and helps me understand how my previous experience of this particular thing fits into the whole picture. So I definitely encourage you to write yourself notes as you go through and do things, and write yourself little technical papers. Nobody but you will ever read them. Think of them as notes to your future self, to help your future self in 10 years' time or 15 years' time comprehend this activity. I definitely strongly comprehend that as strongly recommend that as a side activity to do to help yourself in the future, or to help the people who come after you in the organisation understand how and why some things have been done. That's a value add for the companies to do that. So I strongly recommend that you do that. This is my favourite quote by George Box, and I've already mentioned why I think that's brilliant. Early in my career, when I was doing a lot of modelling and a lot less practical testing, I was always being asked if my models were accurate or if they were correlated, and I was always frustrated that the question I should have been asked was, are they useful? It's not about whether things are correct or super accurate or super correlated. It's if you can make decisions and predictions about what will happen in the future as consequences of decisions, then that is very useful. And the numerical accuracy is a kind of a cost of entry, but it doesn't. It can be surprisingly low, and the models can still be really very valuable. So when I put all of that together, I end up with this kind of very, very simple epithet of, I'm trying to use the simplest possible model, and I'm trying to use it in the smartest way that I can. And so people who know me of old, well, I was forever saying simple models smartly used. It was a nice soundbite that gave people the idea of ruthlessly pursuing the simplest possible model that can answer the question. But using the model as part of some kind of structured experiment, and to understand the design landscape that you're operating in, a simple model is much more valuable for that. So the key question, and kind of the final question really, is when you're thinking about adding something to the analysis, some extra effect, whether it's the flexibility of the monocoque in a multi-body model, or the high frequency dynamic behavior to a tire representation, or some more refinement in a finite element mesh. The key question is, if you do that thing, whatever it is, what decisions will it change when you know the results? And if you can kind of put your thumb in the air and pick a value as a torsion stiffness target, then spending a month preparing a finite element model and putting it in a multi-body model, only to draw some kind of slope which is in about a ballpark as the guess that you made, that's wasted a month. And that month could have been used on doing something significantly more valuable. So this is really the kind of the question that you need to leave yourself with and filter things by, I would say. So I believe that is the end of my presentation. I have spoken for approximately half an hour. We now have some time for questions. So I'll stop sharing. In fact, I won't stop sharing. I will just go back to this slide because it plays videos and I quite like playing videos. But I will now, I'll now invite Sarah to give us any questions that have come in from chat, and also any other questions that anyone's got.
Thank you, Damian. If anyone would like to ask a question, please feel free to enter it in the group chat. We've not had anything through as yet, so we'll just give you a couple of minutes just to enter any questions you have for Damian into the group chat.
While people are just maybe thinking and writing, one question that I had that came to mind, Damian, was to deal with or how, in your experience, you've had to maybe overcome those perceptions that people have about accuracy, and how you've maybe changed their minds. Maybe they were maybe they were modelers, maybe they were analysts, or maybe they were test engineers who were asked to generate measurement data, or maybe it was senior leadership individuals who you had to convince of the benefits of this mindset.
So I wish that I had some kind of fantastic method that I could just lay out as a sort of a killer strategy to convince anyone and everyone. But I don't. It tends to be something that you just have to approach on a case-by-case basis. There is an example that springs to mind. When I was working on the rally team, the Impreza rally team, we were doing a lot of work on dampers. There was a lot of difficulty at one point with getting good performance out of our damper suppliers, and it turned out that the basic problem was that we didn't know what was good performance and what was not good performance. And so I set about a modelling exercise that was entirely theoretical, a quarter car model, but very non-linear. It had a whole load of kind of non-linear things in it that we really cared about. And I reported a number of much traction. But then I was on a test, and I was working with a brilliantly talented event engineer called Tina. And she was fantastic at instrumenting the car in all sorts of interesting ways. And she would always ask me, what am I curious about? And then she would find a way to get data from the car about that thing. And so we've been doing a lot of work on the vertical dynamics of each corner. And she had a large amount of data. And there's a quite a common way that event engineers are used to looking at damper displacement data, in particular, a kind of a combination of displacement and velocity. And sure enough, she had that on her screen in the Atlas data acquisition system that we were using at the time. And so just kind of very quietly, I went back into my model and I shot the output. I made it so that I was plotting the same thing against the same thing. But even more trivially, I changed the colors of the display. The Atlas system had a black background and presented the data as kind of light colors on a black background. Model, as is very common in the analytical world, had a white background and the data in dark colors on that. And so I made that change. I didn't make any. And then I put the laptop next to Tina's laptop while then reviewing the results of this test with someone quite senior in the company. And they looked at the two and said, "Oh, is that the output from your model?" And I said, "Yeah, yes, it is." "Oh, it matches reality really well." "Yes, it does." And in that little moment, I got this huge boost of credibility. And in truth, all I had done was change the colors of the display. So sometimes it takes something small to just encourage people that things are credible. And sometimes it's an uphill struggle. And I think you just fight each battle as it comes. And I certainly haven't got a universal strategy, but I've never forgotten the step in credibility that my work took just by changing the colors. And so I think maybe the lesson is that you need to meet people where they are when you answer their questions, and not be, not try and drag them to where you are, but actually go to where they are and answer their question.
Thank you, Damian. We have had some questions in now. The first is, what is your opinion of digital twinning in the automotive world?
That's a really interesting question, because when people talk about a digital twin, the implicit in the definition is this idea that it either is a digital twin or it isn't a digital twin. And so it completely disallows my idea of a sliding scale of accuracy and a level of error. And a lot of the people promoting this digital twin idea are the people selling the software that makes very complicated models. And so it's very much in their interest to promote this idea. But I'm not sure. I think I think maybe it has some uses in some environments where the use of the device, whatever it is, the vehicle, the aircraft, or whatever, is comprehensively logged and very well known. Then I think there is some value in that. But for something like a World Rally Car, for example, where you can't possibly gather enough information to record what's happened to the real vehicle, the idea that you've got this incredibly complicated model allowing you to make knife-edge decisions, I think is a bit of a fantasy. So I'm very skeptical about digital twinning.
We've had a further question from somebody who missed the start of your presentation, so you may have already covered this. Can you comment on the benefit of hybrid models, experimental analytical models, in the complexity usefulness curve?
Yeah, so I think that there is a class of things where a sort of a first principles causal model is very, very difficult, and in my world, tires and dampers both fall into that category. If you look at some of the video in the bottom left where the cars are kind of screeching around, the behaviour of the tyres under these circumstances is hugely non-linear, is massively temperature dependent, and dependent on a whole load of things that are very difficult to capture in a causal structural model. So the typical approach is to actually get some real tyres, to make some real tyres, and to put them on a tyre test rig and measure what they do under certain circumstances, and then empirically take that measured data back and fit it to a model which is not a first principles causal model, but is some kind of empirical representation. Vehicles like or techniques, I would say, like the multi-body models, both the drifting motorcycle and the drift, it allows us to explore those regimes effectively using experimental data. And so, a lot of vehicle dynamics modeling uses quite a lot of empirical data like this, and dampers are very similar. And there's a number of different levels of complexity of model that you can choose to apply that experimental data to, and it's definitely unless you're a tyre manufacturer and you really care about how the angle between the plies or this compound versus that compound affects the performance, it's definitely helpful, I think, to use this sort of empirical hybrid approach.
Thank you. And how did you manage to keep the tyre radius the same in spite of recommendations from your consultants? What analysis was performed to back up your views?
I was really hoping someone would ask about that, actually. So this was it was really interesting because I didn't have time to do a hugely comprehensive study. And so I did things. One was I looked at what vehicles are out there already. And one of the examples was a Mercedes Sprinter van, which was in a comparable weight class to the vehicle that I was talking about, and has change in weight distribution from unladen to laden. And in particular, when it's laden at GVW, it can have a very unfavorable weight distribution. It can get down to kind of 42% front weight, something like that. And yet it does use the same size tyres. So regardless of what those tyres actually are, it clearly is possible to engineer a vehicle because that vehicle exists. And, we can all jokes about white van drivers, but one of the things it does prove is that those vehicles don't appear to be speed limited by anything other than the laws of physics. So it is possible to make a high-speed vehicle with a tail-heavy weight distribution, even though the classical calculations all suggest that it's something we should be cautious about. And so then the next thing I did was a very simple exercise with a very, very reduced parameter vehicle model, a single track model that many of you will be familiar with. But the time domain solutions for the model, not so much the eigenvalue or the steady state results. And I also added to it a static roll degree of freedom so that I could take into account the roll moment distribution and its effect on the cornering stiffness of the tyres. And so with a very simple two-parameter reduced Pacheco model and a static roll degree of freedom, I was able to illustrate that the behaviour of the vehicle is convergent. And for sure, there are big phase delays as you go very fast and the vehicle is laden. But nevertheless, the vehicle is controllable. And in fact, the difference that the extra tyre sizes would make was a much smaller difference than the difference in character over the speed range of the vehicle. The base variation with speed was much bigger compared to this design decision. And given the huge cost savings that it gave us, somebody recommended that we go away from the staggered tyre sizes. And when we put the prototype vehicles, we ran them right up to 120 miles an hour with no stability issues whatsoever, and developed that was the design top speed for the vehicle, and developed a very pleasing kind of ride and handling balance. So it was a very simple model. It was the first thing was just Googling some stuff on the internet and calculations to understand the weight distribution. And then a very simple Excel-based single-track vehicle model that I already had anyway. Could just parameters. So it was to kind of maybe 36 hours until I was able to support the design decision with. And that was for me, that was a really good case study of this whole myth of accuracy thing.
It strikes me this thinking works on a wide range of timescales, days, weeks, months of analysis, and also at the tens of milliseconds in a real-time controller. Do you have any thoughts on applying this thinking to real-time control, perhaps MPC, where you have found success?
I'm going to say yes. I think that observation is really astute. That this is quite a sort of a scalable, and anyone who's involved in real-time control will know that the real world is infuriatingly noisy when you start to measure it in order to use feedback. The more kind of robust and simple you can make the things that you're doing, the more likely you are to generate sort of smooth output from your real-time control system and to make vehicles that feel over-controlled to a human. Humans work on a bandwidth of up to maybe 5 hertz for sort of hand inputs. And so if you put a real-time controller in that is kind of fussing around with activities at sort of 10 or 15 hertz, it can sort of hard and artificial to a human that's involved in the system. And so in any case, quite a lot of filtering down the outputs until you get something that it fits with what a human might expect. Because if there's not a human involved in the system, then that doesn't matter so much. But having kind of understood, it does of course make sense that rather than doing a very complicated real-time calculation and then filtering it down afterwards, you could just do a more simple real-time calculation. And a really great example of that is the little red car in the bottom left video. This was this car never made it to production, but the embodiment of it turned into the torque vectoring system in the Mark II, not even Mark II. Anyway, whatever the latest Focus RS is, this was a Mark I Focus with a prototype 300 horsepower engine and a torque vectoring system, a front to rear torque vectoring system, and slightly side to side. The real-time control was very simple. It basically chased the linear yaw rate gain of the system in order to keep the car following the steering wheel. And the computational budget of it was very, very small. And it was able to ride over all of the noise on the sensors because it was such a smooth model that you didn't have to do anything fancy. And so it produced really great outcomes in terms of what it felt like to drive. So yeah, it's a very astute question, and I do think it carries across to real time.
We've got 3 further questions that have come in. You referenced a paper you wrote about symmetric versus asymmetric tyre fitment. If this isn't strictly confidential to your employer, would you be able to share the contents with the audience?
Yeah, I think I can probably kind of sanitize that and publish it. Because I think it's quite an interesting. In the original written paper that I did that accompanied this, I said that I kind of came up with a fictional tyre whip example, but this was a real world embodiment of really exactly that. In fact, it honestly made me laugh when when it emerged that this question needed answering. So I've got a large amount of kind of material and notes on that I could be sanitized and put together into a little case study. Yeah, I'd be happy to do that.
That's great, thank you. A lot of predictive techniques aim for a yes-no decision by comparing a simple inaccurate answer with a simple hopeful limit value. Do you believe that statistical predictions of the probability of an event are more or less helpful?
More, definitely more. Emphatically more. One of the things that kind of drives me nuts is when people have got some arbitrary target that they can't really justify and can't really explain, and they use it as a pass-fail gate, and then they use very, very complicated models to try and kind of calculate very accurately whether or not they're near this arbitrary target. And I see that again and again and again and again in multiple different applications. And so what I try and do is I try and talk people into using sort of a fuzzy logic type of thinking. And to give you an example, if we talk about the roll stiffness of a car, for example, I might say something like, well, for this car in this market segment, a 3 degrees per G roll gradient will make me 10 out of 10 happy, and a 5 degrees per G roll gradient will make me 0 out of 10 happy, and in between is in between. And so then we've got this kind of sliding scale, and we can balance. And I think when you've got multiple objectives, trying to formulate a sliding scale like that really helps you in multi-parameter optimization, because you can understand that perhaps for some reason you actually need to give away some roll gradient in order to get some better grip. That was often the case on the World Rally Car, and in the end, there is no 10 out of 10 result for grip, just more. And so if you could persuade people to accept a little bit more roll under some circumstances, but talk to them about how it improved the grip, then you can make significantly more intelligent decisions, I think, on a sort of multivariate framework. So yeah, absolutely.
And one final question. I currently have a lot of output from my simulation, shiny charts and graphs about the behaviour of the system I am designing, but we don't have an historic correlation to tell us what is a good behaviour like, just like when you explained the case of the dampness on the Impreza WRC. Do you have any suggestions about what to ask or supply as input to test demo drivers of earth-moving machines?
Wow, what a fantastic question. Right up until the fact that you revealed it was an earth-moving machine, I was brimming with ideas. I almost think there's a case there for getting a group of people who drive them together, maybe giving them beer, maybe not giving them beer, not if they're going to then go and drive, and saying, what does a happy day look like for you using one of these machines? What does a sad day look like for you? What do you value and what do you not value? And also for the operators. I mean, for the operators, it's relatively simple because it's just about how available is the machine. If it's kind of 100% available, then that's heaven. If you've got 3 of them and one of them is always out of service waiting for parts to be repaired, then that's clearly not heaven. And payload and speed. So you can just talk about the sort of an overall capacity. But I think from the operator's point of view, I definitely think there are differences. And in fact, not long ago, I received on my video feed, as we all do, people don't send me videos of kittens, they send me videos of things drifting. And I received a video of a huge articulated quarry truck drifting around to the loading bay because the driver had decided that this was actually the fastest way to turn it around. And, it looked very beautiful to me. And if this really is a legitimate technique and is not someone cowboying, then it's worth understanding that. But I think there has to be a conversation kind of with the target audience. It was always very difficult for me doing circuit cars because I had to work vicariously through the driver and talk about what do you like, what do you not like, and then try and understand also what made the car faster. Whereas with the rally cars, I had this fantastic luxury of just being able to sit in the car with the driver. And the drivers are fantastic because they can just talk while they're doing all of this stuff, and they can just say, I wish you wouldn't do that, or I quite like that bit, or all of that sort of stuff. So I think there's a very human aspect to talking about what people like. And then there's some engineering into saying, well, what are the engineering metrics that might help us deliver that robustly? That's a really excellent question. I'd be happy to be fascinated.
Wonderful. Well, I think we've all had a good time. I certainly have. So thank you very much, Damian. That was really useful. Thank you everyone for attending. Just a reminder, if you haven't put yourself down to be on our mailing list. Sarah has once again put the relevant email in the chat. So please go there and copy that and make sure that you're kept up to date with the next webinar. We also have our page on LinkedIn, so please connect with us there as well. And you'll hear more about what's happening within the Engineering Integrity Society as a whole. And yeah, I think that's probably about it, unless there's anything that I've forgotten, Sarah. Wonderful. Well, thank you again for all attending. Thank you very much, Damian, for your insightful and really inspiring presentation. And hopefully everyone will find that useful going forwards with their day-to-day work. I think I certainly will.
Oh, thank you very much. It's been an absolute pleasure. Thank you for inviting me again.